Thank you very much. And thanks a lot for the invitation since I was in the area. So it's very nice to be able to come here and tell you a little bit about some part of my research at MIT in the quantum engineering group, mainly named like that just because nobody can spell my last name, so call it Cappellaro group would have been quite bad. What I'm going to try to do today, and it's actually the first time that I give sort of this type of talk, is to try to combine two different research directions which are going on in my group and try to sort of put them together. So hopefully I will do an okay job with that. If you want, the common umbrella is that we are really trying to control our quantum system. And one of the main tools that we use is Hamiltonian engineering. So try to modify the Hamiltonian which is given to us by nature in order to achieve some different task. And the type of task that I will be focusing on today are both sensing and simulation. And hopefully, this sort of resonates with research that is also going on here at JQI. So the first thing that I'm going to talk about is, it doesn't work anymore?
It's the one that says down.
Yes. That's it. OK. So the first thing that I'm going to talk about is quantum simulation. And here, what we are focusing on in my group is really to try to simulate some desired dynamics in what is called, if you want, analog simulation. So we start from some physical system, which has its own internal Hamiltonian, and then we try to add some control in order to generate, as we will see dynamically, a different type of Hamiltonian which can simulate the interesting physical processes. And if you want, we sort of come to this research direction from a very, very common and simple problem, which is probably in your mind a bit different, which is dynamical decoupling, or the task of trying to sort of decouple your system from noise. But you can think of dynamical decoupling in the same way as some quantum simulation task, in which the task that you are set off to do is actually to simulate the null Hamiltonian. So you have some either internal Hamiltonian or some coupling to some noisy sources. And what you're trying to do is to say, well, I want to completely erase out my Hamiltonian and try to just generate a zero Hamiltonian. And how can we do this? It's relatively simple. This has been taught to us from Irving Hahn back in 1950. You can use a very simple sequence, which is called the spin echo. And so you let your system evolve for some time, and then you invert the sign of this evolution. This is simply done if your evolution is of the type of, for example, sigma z. And so on the second half of your evolution time, you're actually evolving under the opposite Hamiltonian minus sigma z. And so on average, over this total time, what you obtain is an effective Hamiltonian, which in this case is very boring, if you want, is just equal to 0. Okay. So this is, if you want, the simplest possible way of trying to engineer some Hamiltonian. So what I'm trying to engineer is this 0 Hamiltonian. And how do I do that? Well, instead of looking at instantaneous Hamiltonian over the whole time, I just fix it some stroboscopic time, like at my final time here. And what I would like to have is that during this total time, I have an effective average Hamiltonian, which is the desired one. So if you want, is a way of dynamically engineer some Hamiltonian over a certain period of time. And as I say, this was, if you want, first introduced in NMR. My background, actually, from my PhD is in NMR. That's why I start from this. But it's, if you want, it can be generalized to much more complex tasks. And if you want, instead of just doing dynamical decoupling, you can try to engineer some more interesting Hamiltonian, which might be able to achieve this type of quantum simulations. So why would one try to sort of use Hamiltonian engineering for this type of quantum simulation? Well, the idea is that I think that I don't really need to illustrate why do we want to do quantum simulation, especially to this audience. But why would I want to use this type of, if you want, analog simulation through this Hamiltonian engineering? Well, the point is that very often in the system that we have, we might just have some restricted type of control. So if you had a nice quantum system, for example, something like a quantum computer, we would be able to just manipulate each individual qubit. And then it's well known that through gates, quantum gates, it's possible to achieve, if you want, a digital quantum simulation. So you can just simulate any possible physical process by just combining in a quantum gate circuit in a correct way. In the same way that you do it on a classical computer. So on a classical computer, when you do simulation, you basically string together a sequence of classical gates, which in the end give you the correct answer. For quantum computers, we know that it's probably difficult to do it, at least until now, unless you have a system of 2-3 qubits. And so what we would like to have is a different strategy. So instead of trying to have just a sequence of C0 and NOT gates, etc., what we try to do is just to take the Hamiltonian which we have in our systems and transform it into another Hamiltonian. So because of that, what we can do is to sort of leave, even if we don't have full control on each individual system which compose our larger quantum system. So very often, the available control is restricted. We might have some type of, for example, collective control. And still, we would like to be able to sort of engineer some interesting Hamiltonians. So one particular example of this strategy, of this Hamiltonian engineering strategy, we apply to achieve quantum information transfer in a linear chain. So the idea is that you will have some excitation on the fourth spin of your chain, or qubits if you want, spin 1/2. And then this can transfer to the second spin in the chain, for example, by this type of Hamiltonian, just a flip-flop Hamiltonian, which transfer the excitation. However, in the physical system that I have in my lab, and I'll show you in a second which one we are using, this Hamiltonian is actually not there. What I have is the so-called dipolar Hamiltonian. So my spin 1/2, they just interact as a small magnetic dipole. And so in a large magnetic field, this is the type of Hamiltonian which I can see. So how can I achieve this Hamiltonian here, which I need for transport, if I only have this other Hamiltonian? As a matter of fact, if I only have collective control, I cannot even, with any approximation, achieve this Hamiltonian here. What I can do is to get this other type of Hamiltonian, which looks a bit weird. It creates two excitations at the same time. So you would not think that this is able to drive this type of transport. But if you're also choosing your states in a particular way, in particular focusing on mixed state, actually this Hamiltonian is pretty nice for quantum information transport. So again, instead of encoding your information in one excitation of your spin chain, you can encode it in, for example, the state of 2 qubits, and then let it evolve under this double quantum Hamiltonian along all your chain, and that correspond to transferring the information from one end to the other end of the chain. So again, I would like to generate this Hamiltonian with my method of Hamiltonian engineering, but I have this other Hamiltonian. So what can I do? Well, one thing that you can try to do is something similar to this spin echo idea, which I showed you 2 or 3 slides ago. So again, the idea is to apply some collective control to all my spins and trying to see if over a certain amount of time, on average, I have my system which will evolve as if it were under the effect of this other desired Hamiltonian. So to see that, what I did is to rewrite my dipolar Hamiltonian in a slightly different way. It's just same as before, but I just separated out the terms. And when written like this, what we see is that this Hamiltonian contains this double quantum Hamiltonian. Again, this can be written as just this other combination of polymatrices. And then it has an extra term, which in practice what I would like to do is just to erase it, in the same way that I was erasing part of my Hamiltonian with the spin echo. And so I can use a very simple sequence, just 2 pulses here with correct timing. And what happened is the following. So if I describe my normal dipolar Hamiltonian as this arrow along the z direction, because it's the part which commutes with my larger Zeeman field along the z direction. Then I rotate it by these force poles, and this now will be another Hamiltonian, which is the same as the dipolar Hamiltonian, but now aligned along the x direction. And then what I can do is just to go between the two very rapidly by doing these pulses here. And on average, I will evolve under the average Hamiltonian over the time period. And so on average, we obtain this, double quantum Hamiltonian. Of course, this is true only to first order, but then what I can do is to have a bit more complicated sequences, many pulses, and I can try to improve my control again, so that, for example, this sequence is sort of it's symmetrized, so any odd order correction just get erased. It's sort of compensate for the fact that the pulses are not instantaneous, and so on and so forth. And this type of Hamiltonian engineering really can draw a lot of ideas from old theories in NMR, in which they've been able to really sort of generate rules in order to have better and better approximation and better control on these complex many-body Hamiltonians. Again, using this type of sequence, I can generate on average over the cycle time my desired Hamiltonian. And as I say, this type of double quantum Hamiltonian actually drives quantum information transfer in mixed state. So when my chain, instead of being in the totally polarized state, is actually in the totally mixed state. But still, even using this totally mixed state, you can still transfer real quantum information and even entanglement, as long as you encode it in correct 2-qubit state, for 2-qubit logical state for each real qubit state. So how do we sort of test these ideas and trying to implement it in practice? As I said, what we do is to go back to my background in NMR and really use just NMR techniques. And we have a very old-fashioned NMR magnet, which was sitting in MIT stairwells for a few years. And we just resuscitated it, and it gives us quite nice results. And why using NMR? I mean, I think that probably trapped ions would be a better system. But what this kind of system give you is really, if you want very good control on this system, and we can really use all these ideas which have been developed in NMR for the past 50 to 60 years. And so we can achieve very, very good control on the system itself. And also we have long coherence time because we are using spins, and so they inherently are quite protected against any type of noise. The other nice thing is that nuclear spin are, of course, we use crystals, so they have in very precise position inside our lattice, and that sort of is a complement to the other physical systems which I use, which are NV centers and other defects in diamond, which are instead typically sort of at random inside the diamond itself. So we are sort of using this system in order to learn how to control these linear chains, and then we hope at some point to sort of jump into the diamond platform in which you have much more flexibility. So what we do is actually to use a system which is FluorApatite. It's just a crystal. You can find it in your teeth and bone. But you can also find it on either eBay or Etsy. You just buy a pendant for $10, and then you have a very nice crystal which you can put inside your magnet. And the nice thing about this particular crystal is that it has this lattice structure in which what you have is an hexagonal lattice, and then if you consider a few lattice structure on top of each other, you see emerging these linear chains of spins which are packed close together with respect to the distance to the next chain. And because of the coupling go as I think this is not supposed to be B, but the distance cube between the spins, what we have is that the coupling inside the chain to the coupling outside the chain is about a factor of 40. So to all effects, when we drive our system, we really see a one-dimensional dynamics even if at some points this breaks down, and we can also explore more interesting dynamics due to the fact that you have other spin in the lattice, I think that we are looking at right now, or the fact that you have coupling to other chains. So using this system, what we can do is really to study evolution under the natural Hamiltonian. What you would see is a very fast decay. It's not really noise or decoherence, if you want. It's just you're evolving under a very complicated many-body Hamiltonian. And what you're looking at is only a very small part of your Hilbert space. So if you want the state that you create populates a large part of the Hilbert state under the many-body Hamiltonian, and you're only looking at the polarization. And that decays down very quickly. If we add control with 16-pole sequence, which I've shown you before, what you can do is instead to recover this coherent evolution for much longer time. And this evolution is actually indicative. You see that we can have also an analytical model for just nearest neighbor coupling in 1D system. And so the evolution is indicative of this, in this case, it's just classical information transfer. But we can also, as I said, encode the quantum information on two-body terms. And we have a slightly more complicated evolution, which indicates that we're really doing this information transfer in our linear chain. However, as you see, I still have some sort of decay of my correlation. Again, this is not real decoherence. Is again, what we are doing is just to look at one particular observable, and we are actually populating a much larger part of our Hilbert space. So we don't see everything, all the coherence, which is still there. But this is also bad because, of course, here what I would like is that at some point when I reach my end of the chain, I will have a revival of my polarization at this other end of the chain. And unfortunately, if I just take the Hamiltonian, which is modulated by my pole sequence, but in some sense given by nature, what I have is particular coupling strength among the spins themselves. And so what happens is that even when I simulate an ideal system, if I have that all my coupling, my nearest neighbor coupling are all equal, as they would be if the spacing among the spins is just constant, then I have a type of dispersive transport. So when I reach the end of my chain, I still have this revival, but it doesn't go back up to 1. It sort of decays a little bit down. And if I want to go even for longer distances, I will have, again, the fidelity of my transfer becomes smaller and smaller with the distance. So what I need to do is, instead of using this equal coupling, all the spin are coupled, the nearest neighbor are all coupled equally, I need to engineer some particular type of coupling. And unfortunately, the dependence of the coupling on the spin position is sort of weird. It's this square root of j n minus j. So it's for a physical solid-state system, what it would mean is that I would have to put my spin in precise position so that because of their distance, that gives me this type of coupling here. Maybe it's possible, and then you would have this perfect transfer. You see, every time that you reach the end of the chain, you recover perfectly your excitation. And so you would recover perfectly this quantum information that you encoded in the excitation itself. But I would say that this is quite difficult to achieve if you want a hard engineering method. So what we would like to do is instead to apply these ideas of Hamiltonian engineering, adding some filtering in it, and try to achieve this type of coupling in a dynamical way. So if you wanted to resume a little bit, what we want to do is the following. We start from the natural Hamiltonian. Then we apply some control in order to achieve the desired type of interaction with, for example, this double quantum interaction or the Hamiltonian for your spin transfer. And then what you would like to do is, for example, to remove any unwanted couplings. Our perfect transfer only happens if you have only nearest neighbor coupling. But of course, for dipolar coupling, you will have also all the other coupling to all the other spins. So you would like to remove this type of coupling. And then in the end, engineer the strength of the remaining couplings so that they give you this ideal optimal coupling strength, which in turn can achieve this perfect transfer. And so one idea that we had in order to achieve all of this was, again, to add some extra control on our system and trying to see if on average over the course of the evolution we can achieve this ideal Hamiltonian with the optimal coupling. To do that, what we do is to alternate evolution under the double quantum Hamiltonian with evolution under a magnetic field gradient. And that encodes some extra phases on each of the coupling that we have in our Hamiltonian so that we can sort of modulate the coupling strength of each coupling among the spins. Then by choosing in a nice and appropriate way the timing of this coupling, what we can achieve are some nice type of filters. So the first thing that we would do is to choose the coupling so that only the couplings which are the strongest one, the nearest neighbor coupling, have maximum intensity, while all the other coupling which are in between, in this range here, are just average to 0. So the next nearest neighbor coupling will just be average to 0. You have some small correction for the other more distant coupling, but of course they're already smaller to start with. Then what we can do is to, again, play around with this timing here and choose them in a correct way so that we further modulate the intensity of the coupling according to our law that we would like to achieve. And in this way, our total filter looks something like this, in which each one of the nearest neighbor coupling now are non-zero and also modulated by the desired optimal coupling modulation. And in this way, by this, if you want a dynamical filter, over the cycle time of our evolution, we have this optimal Hamiltonian, which can drive perfect transfer. So of course, this is just an example, but similar ideas can be used to engineer many types of Hamiltonian and also different geometries but not the spin chain. You just need to come up with the correct filtering actions in order to really get the correct couplings among your spin that you would like to achieve. And so, okay, I already said we can really achieve this perfect quantum information transfer. And the other thing is that we only applied, if you want, a global control. So all the pulses were applied the same way on the pulses. And the thing that we did was to sort of add this extra magnetic field gradient in the z directions. So up until now, what I talked about was really how to engineer this Hamiltonian evolution with particular example of this quantum information transfer. Yes?
Can I ask you, it's probably a dumb question. If you go back, and you said if you have equal couplings, you get dispersion.
Yes.
In the transport. Is there an easy way to see why that is? I mean, I'm just thinking classically, I mean, the classic, masses in springs, you have no dispersion, right? You can transfer it.
Yeah. I mean, so if you look at the dispersion relationship, it's clear that you will not.
So these are qubits, not masses in springs.
Yeah, but you can still you can still go in the limit to where this distance between the spin is very small, so you can sort of treat it as like a continuous qubit string, and the dispersion relationship is linear, so you don't get.
Is that square root of J and minus J obvious?
No, I mean, not to me. So, historically, it actually comes from atomic physics. So if you have like a large spin, like a spin n, then so this is like the same condition that you need in order to transfer from plus n to minus n. And then you can reproject that condition onto, if you want, your linear chain, or more generally onto hypercube, which represent these chains, and you get this condition. And this was found like back in 2003 by Bose and all. So. But yeah, it's not, I mean, a posteriori it's clear, but it was nice that we found it out. Okay, so we have this first, I think, nice application of this Hamiltonian engineering, which was in this simulation. And then what I would like to talk for the remainder of my talk is instead how we can use similar ideas of, if you want, Hamiltonian engineering, and in particular creating these filters in order to do quantum sensing. And I can really go back to the same picture which I had at the beginning for Hamiltonian engineering, which is this spin echo sequence. And again, this spin echo sequence, it was originally introduced in order to be able to refocus quasi-static dephasing noise. And so if you're trying to, for example, measure also some external field, you will also completely erase the effect of the external field. However, if the field that you want to measure oscillates in times, the effect of this field will be, of course, preserved because the sign into these two time intervals, if you remember, they were opposite one to the other, and so the phase accumulate adds up constructively. So really what you have is that you sort of have a compromise between how much signal you can get coming from the field that you want to measure and how much noise reduction you can achieve thanks to this type of decoupling sequences. But as you will see in a second, that's not only the thing that we are interested in. So sure, there is this compromise, and that's quite important, and I think it's quite general if you want in quantum sensing. But there is some extra information that you're actually gaining when you apply this type of dynamical decoupling sequences to your system. So let's look at these two different points. So the first point, as I said, is that every time that you want, for example, to sort of quantify how well you're measuring something, what you're interested in is the sensitivity, or if you wanted a minimum field that you can measure. In this case, I'm thinking in terms of magnetic field because I use typically spins. So for me, it's the typical. So these are simulations for MV centers with a particular noise model. And so typically what you look at is what is the minimum field that you can measure as a function of how long you're actually trying to measure it. And of course, you have single qubits, so you have just the typical 1 over square root of the time, okay, type of dependence, which is given by your shot noise. And this is unfortunately interrupted as soon as you hit the coherence time of your qubit sensor itself. So I would continue to go down as 1 over the square root of time if I measure longer. But unfortunately, because I have noise, my signal decreases exponentially. And so my signal-to-noise ratio increases exponentially at the same time. So what I can do to sort of try to go beyond this limitation is to apply some of these decoupling sequences. So instead of just one pi pulse, I can apply an extra pi pulse, and hopefully this will give me a slightly better coherence property. Typically because what I can do is to refocus not only completely static noise, but also noise which is fluctuating sort of at the time scale comparable with the distance between my pi pulses. So I add an extra pulse. Now my coherence time is a bit longer. So I see this exponential decay, exponential increase at a slightly longer time. And so correspondingly, the sensitivity, because I can go down with this 1 over square root of t for longer, is slightly better. And I can keep doing this. I can add some more pi pulses. Okay. And I have a better T2 time, so I have a better sensitivity. But of course, you notice in my plots that now what I need to have is a field, which I want to measure, which oscillates much more rapidly. And so these curves are also tagged by colors by their frequency. So here, sure, I can have better sensitivity, but only to fields which are on the order of 0.2 megahertz for this particular example. So in general, what you get is that you can not only have this compromise between how much signal you get and the noise, but also between what is your coherence time and the frequency to which you're sensitive. So what we're actually doing is to create a frequency filter by applying these pulse sequences, which will only pick up signal which are at a particular frequency with respect to the cycle time and the pulse distance that we are actually applying. And so we are gaining information not only on the field strength, but also its dynamics, what is its frequency content. And we can, of course, generate colorful plots which tell us what is the sensitivity for each particular pulse sequence. And again, they are color labeled by the particular frequency of the field which is we are optimally sensitive to. And we can use not only pulse decoupling, but also some other type of control. But the idea is always the same. What we are doing is not only to learn something about the signal strength, but also about its dynamics, its frequency. And so it becomes very interesting to be able to generate these filters because they tell us some extra information. And the extra information can be about our deterministic field, so it will be its frequency content, but also about, for example, some noisy field. So what we can do is to use this type of technique, for example, to reconstruct the spectral density of noise sources. So this was an experiment that we did in collaboration with Ron Wadsworth at Harvard, in which what we were looking was to try to reconstruct the spectral density of a bath of electronic spin in diamond using the MV center. And over a year, there's been many similar experiments done in many different groups and also with quite a few of different physical systems. And again, what we want to do is to use these dynamical filters in order to be able to reconstruct the noise spectrum, which then can be used in order to generate, for example, even more optimized decoupling sequences for that particular spectrum, and which will allow us, for example, to sense whatever else, whatever other signal we want to measure, while optimally decoupling from the noise that we really have at hand. So moving beyond these classical sources of magnetic field, or could be electric field or other fields, and also these, if you want, noisy source of noise, what we would like to do is also to be able to sense some quantum systems. And in particular, what my group and other group is interested in is really to try to measure nuclear spins which are close by to an MV center inside the diamond. And the idea is that this nuclear spin could be part of, for example, of a biomolecule or a protein, and really knowing the structure, if not of the whole protein, but at least of some interesting pockets near the surface, can shed light on functionality of the protein and maybe even lead us to developing new drugs which attach to this binding site of the protein itself. Of course, there are many challenges because intrinsically nuclear spin are, if you want, very tiny object in terms of the magnetic field and the signal that they produce. That's why you typically have this large NMR system, or you need to use X-ray crystallography. But beyond the problem of trying to really just increase the sensitivity of NV centers to the nuclear spin, there is also a second challenge, which is the fact that typically proteins and biomolecules are very dense objects. The distance between nuclear spin is on the order of angstrom. So what you would like to do is to measure a very tiny signal coming from a single nuclear spin in the background of many other signals coming from all the other nuclear spins. Because if you want to reconstruct the position, you really need to be able to distinguish signal from individual spins. So how can we do that? So I mentioned MV centers, which you probably by now everybody knows what MV centers are. So I have basically one slide, introduction to MV centers, which hopefully probably don't even need to show, but it's an interlude. So MV centers, for whoever doesn't know yet, are isolated defects in diamond with spin 1, and we can see them. That's the number one requisite in order to be able to use them. But the nice thing about MV center is that they can really polarize optically to very low temperature by just shining green light. And also they have a nice set of electronic levels which allow to have single spin state detection by just looking at the fluorescence light intensity, which depends if your MV is in the 0 state or in the plus or minus 1 state. The other nice thing about MV center is that they have pretty long coherence time, even when you're just considering a natural diamond sample. And this coherence time can be increased if you actually have isotopically purified samples. I don't have a diamond, I just need some. So the MV center have been proposed to be used as a magnetic field sensor. And the idea is very simple. You have just a spin, which acts as a magnetic dipole. And so it will be really sensitive just to the presence of any external magnetic field by its Zeeman frequency shift. So one thing that you can do is just to do, for example, a Ramsey type sequence. And then you're able to measure the phase due to the precession of the spin itself and convert that into a magnetic field. They're also been proposed to be used to measure electric field, temperature, pressure, strain, rotation. And if you have other ideas of what we can measure with MV Center, let me know, but I can add it to the list here. The main advantage of MV Centers magnetometers is that really they can be miniaturized. So what you can do is to bring your MV Centers or your diamond very close to the source of the magnetic field itself. So this is an old picture, and it has been sort of realized in practice. For example, this is an AFM tip with a diamond slab, well, a small diamond, and the pillar fabricated in the diamond, which contains an MV center. And then you can really go around and sort of do the same type of task, which is to scan around and find little, at the moment, electronic spin, and hopefully very soon also nuclear spin. So how can we use this MV center in order to really measure with very high spatial resolution the presence of nuclear spin? So there has been a few different types of scheme proposed. So one is to just consider the nuclear spin as, if you want, source of classical magnetic field, which is precessing because of the Larmor frequency of the nuclear spin itself. And so if you apply some of these dynamical decoupling sequences with pi pulses, you will be sensitive to the nuclear spin, which precesses at the correct frequency. And so in this way, you just have this oscillating field that you pick up the signal coming from this Larmor precession. We can also look at the same, if you want, same idea in a more quantum way. And you really, what you would like to focus on is the coupling between your electronic spin and each individual nuclear spin. Then what you will have is that the condition is, if you want, of matching or being able to detect the oscillation is due not only to the Larmor frequency with omega 0, but also to the coupling of the nuclear spin to the MV itself. And if you adopt, if you want, a quantum point of view, which I like better because I like quantum better than classical, what you're actually doing is to engineer a dynamics of the nuclear spin by controlling the electronic spin. So in practice, what you're trying to do is to generate a pi over 2 rotation of the nuclear spin, and only of the nuclear spin which is on resonance with this condition here, while all the other spin which are not on resonance will have some very small evolution, and so they do not lead to any type of signal. So what you do is to just change the state between of the electronic spin between 0 and 1, and this sort of impart a rotation around 2 different axes for the nuclear spin. And so in the end, you have an effective evolution. And if you start with your electronic spin in 0, you will have one type of evolution. If you start with the electronic spin in 1, you have a different type of evolution. And so when you consider the coherence between the 2 states, you will have a decay of the signal of the MV center itself. So what you get is that, as I said, of resonance, basically the 2 states, 0 and 1, are still very close to each other, while here you have a large difference depending on what was your initial state of the electronic spin itself. And we can actually see this in experiments. There has been experiments from many groups. Here we change the effective frequency of our flip-flopping of the MV center. And when you hit the correct frequency for fluorine-19 or for proton, you see a dip in the coherence, because what you've done is to modulate the evolution of the nuclear spin, and this in turn sort of destroy the coherence of your MV center. This is a very nice result, and they show that you can really measure external spin outside the MV center. But of course, they're not precise enough. So here I have like a large ensemble and very wide line width. So the spatial resolution in this type of schemes is quite limited. Of course, if instead of looking at these very dense ensemble, so this was actually just fluorine and proton coming from the immersion oils, which is used in the confocal microscope for to look at the MV centers. If instead of looking at this very dense ensemble, we use the same techniques and instead looked at very sparse ensemble, what you would see is something quite different. So you really see signals which come from, in this case, I think there were 8 different spins, which were just carbon-13 and the diamond lattice, so they're very sparse, it's 1% abundance only. And so you're really able to distinguish the fact that you had individual spins. And from this type of experiment, you can also extract what is the position of these nuclear spins themselves. So what we'd like to do is to achieve results which are similar to this, but in the presence of a very dense sample. How much more?
How many molecules are contributing to these?
So, OK, so this one, as I say, this is 1 MV center, and it's looking at carbon-13 inside the diamond.
Oh, I see. Well, say on your previous example.
And the previous example,
Oil wetting the sample.
so this is typically, let's say, 3.5 nanometer volume with a density of proton, which is, I'm not sure how much, but it's, yeah. So, yeah, the difference is that really here you start from a very sparse sample, and so you can actually distinguish individual contribution. But even if you use the same exact technique, when it's very dense, you don't get. So how much more time do I have? I feel that I'm running late. OK. So hopefully, I will manage to explain it without rushing too much. So what we did was to try to come up with a slightly different way of looking at these external nuclear spins. And again, the idea was, well, what you really would like to do is just to create some filters which will detect only some spin and not the other one. And in this way, you can increase, by increasing the frequency resolution, you can also increase the spatial resolution because the two go hand in hand. So instead of relying on this type of, well, too far away, this type of sequences with pulses, what we did was to rely instead on a different mechanism. So what we want to do is to sense polarization leakage from the MV center, which is polarized optically, to your system of nuclear spin, which are instead at 0 polarization because at room temperature they have basically no polarization. And so every time that you have this polarization transfer, you know that there was some extra external nuclear spin outside the diamond. So this, again, can be done in a way which is resonant. I will explain in 1 second how. But again, it's not enough to really distinguish individual nuclear spins. So what we did was to say, well, we want to add some extra field gradient. Similarly, in a way that we did, if you remember, in this Hamiltonian engineering for quantum information transport, in order to achieve a frequency filter, which will allow us a better spatial resolution. In order to actually do this in practice, what we did was also to exploit the fact that you have a nuclear spin associated with the NV center. It's just the nitrogen of the NV. And we can use this in order to have an intrinsic long-time memory, which allows us to go for much longer times. So what is the idea that we had in mind? Well, what we have is something like this. So I have an MV, sorry, I'm still learning. We have an MV center here, which is sitting inside our diamond. And then we'll have some nuclear spin outside. So here I'm plotting just 2 of them. And what we have are various coupling between the MV center and these 2 spins. And this dipole-dipole coupling will have some longitudinal component, which shifts the energy of the nuclear spin themselves, so a frequency shift. And then you also have some transverse component of this coupling, which does this flip-flop, which can drive polarization exchange between the MV center and each individual spins. And then, of course, there is also coupling among the nuclear spins themselves. So the first thing that we want to do is to try to separate in this frequency axis the nuclear spin. And to do that, what we can do is to add some gradient. The gradient can be actually just provided by the MV center, or you can think of adding some external permanent magnet or having some extra electronic spin on the diamond surface. And what this does is to really separate in the frequency axis the 2 spins, and so make it a bit easier to distinguish the 2 of them. But again, this might not be enough to give us this single spin spatial resolution. So what we do is to add some control. so that we create this filter which will erase the coupling among the NV and one of the two nuclear spin, and only retain the coupling to the other spin. So this is very similar to this idea that we had to engineer the optimal coupling for the chain. So we do a filter which will erase coupling which are not on the exact resonance. And then finally, we also want to eliminate the coupling between the two nuclear spin because they just increase the line width and sort of spoil our frequency resolution. How to achieve all of this? Well, the spin sequence, the pole sequence is slightly complicated. But bear with me, it's easily explained. So we just initialize when we read out at the end. And the two important ingredients are this spin lock term, which drive the polarization exchange, explain in a second how, and then evolution under a gradient, which impose this extra phase rotation, which in turn create the frequency filter. And we alternate between these two types of evolution in order to achieve this nice frequency gradient. And of course, we also control the target nuclear spin in order to decouple from each other. So how can we achieve this polarization transfer between the NV center and the nuclear spin in a resonant way? Well, what we would like to do is to use this transverse coupling to achieve this flip-flop between the spin, which will transfer the polarization from the NV center to the nuclear spin. But of course, the energy of the NV center is on the order of gigahertz, while even with high field, the nuclear spin have energy on the order of megahertz. So in principle, I don't expect any exchange of polarization between the two of them. That is actually nice because it allows me to introduce this polarization exchange only in a resonant way. So what I do is to apply an external driving field onto the NV center with a frequency which will match the particular frequency of the spin that I want to polarize. And now in the dress basis of the NV center, the two spins have the same exact energy, and this polarization exchange can now happen. And so this, I can achieve it in a way which is frequency sort of selective, and is also compatible with the nuclear spin decoupling, while these other pole sequences are a bit more difficult to integrate with nuclear spin decoupling, and also protect the NV from external sources of noise, because basically what I'm doing is a string of pi pulses so close to each other that I have now a continuous driving. So this is another way of achieving long coherence time on the order of milliseconds. So now, because of this driving, what I have is that I'm reintroducing this type of coupling between the two spins. We drive this polarization exchange. So instead of just letting my system evolve under this coupling, I alternate it with this magnetic field gradient. And so each one of the spin, of the nuclear spin, will evolve under this gradient and pick up an extra phase. Again, I can choose the timing and repeat this polarization gradient in a way which will create a nice filter which will only select some spins which are in resonance with the particular timing while canceling out this type of Hamiltonian for all the other spins which are not in resonance. And this really allows me to achieve this very high frequency resolution. And I can apply this type of gradient for a long time because I can store the information about the NV state onto the nuclear spin while applying this gradient. And so this allows me to go beyond coherence time of the NV center and up to millisecond time scale. OK, so the rest is just an illustration of what we can achieve with this type of technique. So we did some simulation in order to show that actually you can do it on a physical system. We picked some protein which seem to be interesting because it's involved in various different drugs which can attack from Alzheimer's to HIV. And we just picked one particular ligand, this 11 spin here, which, again, were sort of targeted for possible drugs. And what we did was to simulate our control Hamiltonian, and the type of spectrum that we achieve looks something like this. Every time that you see a dip, it means that you had a polarization exchange from the NV center to a particular nuclear spin. And so the NV center is no longer in the brightest state, which is the 0 state, but it has lost some of its polarization. And so you see a dip in the polarization contrast. And thanks to our frequency filter, we can achieve a quite good spatial resolution and frequency resolution, so we can really distinguish individual spins, which would not be possible otherwise. You would have just a broad spectrum going along like this. Of course, this is still not perfect. For example, we have some spins are not resolved because their frequencies are inherently very close to each other because of the structure of the protein itself. But still, using the two parameters, the frequency position of the dip and the depth of this dip itself, we can reconstruct what are both the longitudinal and transverse part of this dipolar coupling. And with that, we can figure out where our nuclear spins are. Unfortunately, as a matter of fact, you only have two parameters per each spin. So what you expect is not to be able to reconstruct exact position of the nuclear spin, but only up to a phase, which correspond to the fact that the dipole coupling itself is sort of symmetric, and so you do not have enough information. But the nice thing about the scheme that we chose, this polarization transfer, is that what you're doing is, sure, detecting the presence of nuclear spin, but at the same time, we're also polarizing them. That's what we're doing. We're leaking out polarization. And so now the nuclear spin is slightly polarized, maybe not perfectly, but they have some polarization. And they can become probes of their own environment. So what we are thinking that it could be possible to do is really, if you want, a three-steps process. So you initialize your MV center, and you transfer that polarization in a selective way to one or two nearby nuclear spin. Then you let the nuclear spin themselves evolve for some time, and that will make this polarization diffuse in the network of your spins. And then we measure where the polarization has arrived, again, using the MV center and this frequency selective method. And in this way, it's possible to reconstruct this type of 2D spectra, which are very common in NMR, and here they're, in some sense, a new addition to our tool set, in which what we see is, of course, this diagonal term, which just means I polarize one nuclear spin, and then I retrieve that polarization from the same nuclear spin. But I also start seeing emerging this cross-diagonal term, which tell me I polarize this spin, and then this spin was so close to spin number 3, which transfers some of its polarization to this other spin, and now detect that polarization from there. And in this way, we can gain more and more information about the nuclear spin network and have a better sort of idea of what the structure of the spin system itself is. And here we didn't put it inside, but I could also go back to the idea about Hamiltonian engineering and trying to engineer, if you want, some optimal polarization transfer in this complex network by modulating in some way the evolution of the nuclear spin themselves. And I think that this is something that we would like to work in the future.
How do you do that? With the field? With an external field? Or?
Yeah, so I mean, we can control the nuclear spin. It's just like ref pulses. And again, if you have this source of magnetic field, which can be the MV center itself, when it's in the one state, it creates some extra magnetic field. And so you should be able to engineer some interesting dynamics here instead of just relying on its own dynamics.
Around your NV, you can play with it.
Yeah. I mean, you can just put it in some like population state, which creates the external magnetic field. Okay, so this is all that I wanted to tell you today. So I really sort of touch on two different topics, which, however, sort of come together by this idea of trying to engineer the Hamiltonian, and very often creating these filters, which allow even better, if you want, simulation of interesting dynamics by using this Hamiltonian engineering for analog simulation, and also allow you to have very high precision spectroscopy, frequency spectroscopy, which can translate into very high spatial resolution, if you want, the nano MRI of interesting nuclear spin systems. I, of course, need to thank the people who actually did most of the work. Actually, I think that I should really point out mostly Ashok Ajoy, who's a graduate student, and he has been really the driving force under many of these ideas about Hamiltonian engineering. Is very creative in how you can figure out clever ways of obtaining any type of Hamiltonian that you want. So if you have some crazy idea of a Hamiltonian that you want to generate, if you talk to him, he can figure out a pulse sequence which will do that. Ken is working on the NMR experiments. Ashok, together with Luke and Kasturi, they built up the experimental setup to actually implement these ideas for nuclear spin sensing. And Masashi and Alex have been working on these ideas of dynamical decoupling filtering for both deterministic and noisy magnetic field sources. So with that, I'll thank you for your attention.